Good morning, girls.
Good morning.
Hey, girls. Good morning and welcome. And before we start with chapter 19, any questions? No questions? Doppler. Okay. And ladies, what Doppler basically is going to be, you are okay. This is okay, it is an ultrasound examination. Yeah, which means that okay, as we use our ultrasound equipments. But the thing that we actually want to measure or record as a Doppler exam is to record the blood flow. Primarily, in the blood flow, the main thing that we were looking for is going to be the velocity. Okay. Where we know that as velocity, that was mainly what we call speed. Plus direction. Is that clear? So your speed is still going to be a numerical value. We can say 40, for instance. That's centimeters per second. Okay. But as far as Doppler is concerned, the direction is going to be written as a plus or as a minus. Okay. So all based on the direction of the blood flow. If it was, for instance, flowing at a speed of 40 centimeters per second, you could have a positive 40 centimeters per second velocity, or it could be as okay a negative 40 centimeters per second velocity. Clear? So these are going to be as okay our Doppler readings. Did you guys get that? And that was your chapter 19. So let's start with chapter 20. Okay. There's more to it. Okay, girls? Now, so please keep in mind, yes, okay, in Doppler. I mean, yes, okay, because the primary goal is to, yes, okay, record the velocity. Clear? And based on that velocity, that's okay, fine, that's okay, establish, okay, as what could be the issues. Okay. And yes, okay, the blood flow, which means yes, okay, may help us diagnose different, yes, okay, vascular abnormalities and so on that the patient may be suffering from. But ladies, please keep in mind, in Doppler, that's okay, the goal is not to achieve an image. Your primary goal will be to, that's okay, record the velocity. Did that make sense?
Yes, it did.
Good. And as I say, that's okay, what is it if we do in Doppler? That's okay, we use our basic ultrasound equipment. So it's going to be as okay, the same transducers, exactly, that we used for regular diagnostic imaging. Yeah, okay. So it's okay, when we do a Doppler exam, if you guys remember, that's okay, on our keyboard we have two, yes, okay, buttons which we haven't turned on yet. Okay. We had this one, this was okay as your B mode, if you remember that one, right? Okay. Over here we had the M mode. And in between those were yes, okay, respectively, yes, okay, color flow. And one was labeled as okay as PW. Okay, which are as okay, two separate Doppler modes. So what mainly is going to happen is that okay, as when you turn on any of these functions here, is okay, it's going to yes, okay, turn on the Doppler functions and actually it's okay, enable you to measure yes, okay, the velocities of blood flow through yes, okay, structures in the image. Is that clear?
Yes.
Right. Okay. Okay. Now comes the question. And the question is, how is this done? Now we can say as okay, we have a transducer. Clear? This transducer here is okay, it's going to yes, okay, transmit sound waves. At a frequency. Right, okay. In chapter 17, we call this frequency here as okay, we call that the fundamental frequency. Right? Okay. In all the previous chapter, we made as okay, just as called as okay at the frequency. Frequency is okay of the transducer. We're just going to say as okay that whatever frequency the sound wave is being transmitted at is going to be referred to as a transmitted frequency. Did that make sense?
Yes.
Good. Let's just say that, okay, yes, in this instance, yes, okay, our transmitted frequency is 2 megahertz. Yeah, which mainly means that, okay, yes, it produces a sound wave which has, that's okay, 2 million cycles per second. Now, the frequency of the sound wave, because, okay, what's going to happen is that, okay, yes, this sound wave here is okay, as it hits structures, it's going to is okay, reflect back. Okay, okay. So what we will have here is going to be as okay, a reflected frequency. Is that clear? Is that clear?
Yes. So the
Good.
sound wave that's coming back is known
Exactly.
as reflected
So
wave.
we are going to refer to that as the reflected frequency.
Okay.
Clear?
Yeah.
Now, if this here was also yes, okay, 2 megahertz, that will mainly mean that the structure here that was being scanning or was being scanned did not move. Okay, and the actual structure which movement we want to check for is the red blood cell. So that's okay. In Doppler, your tissue, or what we will call reflector, is going to be as okay, your red blood cell. Now, what we mainly can say is that, okay, yes, if your transmitted frequency is equal to the reflected frequency, that will mainly mean, as okay, that will mainly indicate that there is no motion, or we can say, okay, no flow of blood. The other example could be that, okay, yes, if we say it's okay, that we started off with it's okay, 2 megahertz. So we say, okay, here was 2 megahertz, and okay, the reflective frequency was 2 megahertz as well. That they remain the same. Now, the other instance could be that, okay, yes, your transmitter frequency, let's say, okay, just keep that at, okay, at 2 megahertz as well. But if the reflected frequency is greater than that, we can say it's okay that it may has okay here be, for instance, let's say any number that's greater than 2. We can say it's okay 2.2 megahertz. Yeah, what that mainly will lead to is that we actually, okay, we'll have something that is going to be called a Doppler frequency. Okay. We will have what is going to be called a Doppler frequency. And that Doppler frequency goes as mainly as, okay, going to be calculated by, as okay, reflecting as okay, subtracting the reflected frequency. From the transmitted frequency. Yeah, we have that's okay. 2.2, from which we as okay subtract 2. So our Doppler frequency in this case here is going to be 0.2 megahertz. Which means it's going to be as okay the difference between your transmitter frequency and your reflected frequency. So based on this frequency here, what the system will say is that, okay, yes, the blood is flowing with it will calculate the velocity at which the blood is flowing. Did that make sense?
Yeah.
Okay. Now we can also have yes, okay, another instance in, for instance, yes, okay, where we say yes, okay, the transmitter frequency was still yes, okay, 2 megahertz. But yes, okay, what if our reflected frequency, for instance, was, let's just say 1.8 megahertz. Now in that case, that's okay, again, we can say that's okay, subtract 1.8 from 2. And we will actually end up with a frequency of a Doppler shift frequency of minus 2 megahertz. Yeah, yes, okay. Still going to yes, okay, use this megahertz here to yes, okay, calculate the velocity. But you're going to have okay, what we will call is okay, a negative Doppler shift. Or we can say it's okay as far as the frequency here is okay, that is mean it's okay, just going to be is okay, calculating the speed part of the velocity. Where we can say it's okay, that 2 megahertz could mainly mean that okay, just randomly, okay, that it was okay, yes, that the structure was flowing at a speed of 2 meters per second. But what it means to be, for instance, okay, what we had here, positive, is that okay, as this moving red blood cell here is flowing towards the transducer. Whereas the negative Doppler shift at the same speed, because the difference between the two frequency was 0.2 megahertz. But the negative mainly will mean that, okay, as it is moving away from the frequency, or from the, transducer at a speed of, okay, that's 2 meters per second. Did you ladies get that?
Yes.
Now, it may sound crazy, but where does this technology come from? Any idea?
The ultrasound machine.
No. There's Doppler technology here. Where did that evolve from? It's okay not to know.
I don't know.
It's not written in the book anyway. It's evolved from, yes, okay, submarines. So submarine technology, or okay, says, okay, submarines have been using, yes, okay, this technology here even before, yes, okay, was implemented in ultrasound as, okay, as to be utilized for Doppler. Just think of it, girls. Now, when you say submarines, what are they? They are mainly, yes, okay, ships underneath the water, right? Did that make sense? Okay. Right? Now let's just say that, okay, yes, we have this submarine here. We mean, yes, okay, in this example, yes, going to consider that this is going to be, yes, okay, the transducer. Okay. Now in submarines, that's okay, they're not going to be able to, yes, okay, get on the deck and look out on the horizon to check if there's any, yes, okay, ships or boats or anything, yes, okay, in the horizon that is approaching them because they're underneath the water. So what was it that the submarines had? They had, okay, as a radio system that mainly as, okay, would transmit our radio signals or waves at a certain frequency. So this is what we hear as, okay, we'll call as, okay, our transmitting frequency. Did you girls get that? Okay. Now they will travel until, let's say, as, okay, they hit let's say as, okay, another structure. Now let's say here that, okay, as it hits another, yes, okay, submarine. But it's okay, in our case, yes, okay, we're going to say that this is going to be, yes, okay, your red blood cell. So I may say about, okay, yes, red blood cell out there, or it's okay, another submarine out there. Now the people on, that's okay, yes, our transmitting submarine or transducer submarine would not know whether this is approaching or traveling towards us, or is okay, traveling away. Well, they will get to know that because if the frequency at which the sound waves are going to, yes, okay, be reflected off back from this submarine here, or what we, yes, okay, will call, yes, okay, or a reflector, which actually is okay, in the case of Doppler is going to be the red blood cell. If that reflecting frequency is increasing, or is going to be, yes, okay, greater than the transmitted frequency, that will mainly mean that, okay, yes, this is moving towards the transducer. Or we can say, yes, okay, the distance between, yes, okay, the transducer and the red cell and the red blood cell is decreasing. Now, since this one here doesn't move, he or she's just lying stationary. This is going to be the one that moves. So based on, yes, okay, the difference in the frequency, they will be able to say, yes, okay, is it moving towards us? Now that's going to be the case if the reflecting frequency is greater than the transmitted frequency. Whereas, now this submarine here is okay, maybe moving away. Or we can say it's okay, or red blood cell may be moving away from the transducer. Now that I mainly call that, okay, yes, the reflected frequency is going to be as, okay, lesser than the transmitted frequency. Did that make sense? Okay, so if you have watched, that's okay, any, that's okay, war movies or something like that, or even, that's okay, documentary, you may hear that, okay, yes, the sound go deet, 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 like that. Now, what does that mean? That the other submarine is approaching. Or you can say, it's okay, that the distance between the two submarines are decreasing. But here, it's okay, one submarine was going to be, as okay, your transducer. The other was going to be the reflector, which in case of Doppler is going to be the red blood cell. So in Doppler, your reflector, the structure that is going to, okay, produce the reflection, is going to be your red blood cells. Clear? Okay. So we can mainly say that we are going to have, as okay, two kind of, okay, as what we can call as, okay, Doppler shifts. We will call it Doppler shift. So we can call it, okay, Doppler shift. This can also be known as a Doppler frequency. Is that clear? But what is it that this Doppler shift or this Doppler frequency here is? That is mainly, as okay, just going to be, as okay, the difference between the reflected frequency being subtracted from the transmitted frequency. Is that clear? Or we can mainly say, okay, just say it's okay, that it will be, as okay, the difference between, okay, let's just, okay, the reflected frequency and the transmitted frequency. Yeah. What was it that our transmitted frequency was going to be? Mainly, as okay, we can just say the transducer's frequency. Is that clear? Is that clear, girls?
Yes.
Okay. Now, what we can say is this Doppler shift, or it's okay, Doppler frequency. Because okay, it means okay, there's going to be okay, the difference between two frequencies. That's why they also call it as okay, Doppler frequency. Or we can say okay, a shift in the frequency. What do you mean by a shift? That it actually is okay, changes. But there were mainly as okay, we can say it's okay, 2 or 3 scenarios. We can say that okay, if the reflected frequency was equal to the transmitted frequency, right? Okay, what that actually is going to lead to is that's going to be as okay, zero Doppler shift, or what we also can call it as okay, Doppler frequency. Mainly because okay, if you had 2 megahertz and you subtract 2 megahertz from that, what you'll end up with? 0. Right, okay. Right, okay. So that's going to be as okay, mainly mean that okay, yes, the reflector here was not moving, neither towards the transducer or away from the transducer. So that mainly means that okay, as we have a Doppler shift of 0. There was no shift in the frequency, or no Doppler frequency, because here is okay, our reflector was not moving. In Doppler, what is going to be our reflector? The red blood cells. Did you girls get that?
Yes.
Whereas, if you said that, okay, yes, the reflecting frequency, for instance, yes, okay, was greater than the transmitted frequency. Okay, which means that, okay, yes. Now, what that will lead to is that we actually, yes, okay, will have what people call as okay, a positive Doppler shift. Now we could just say as okay, that we said 2.2 megahertz, from which 2 megahertz was subtracted. So we end up with, okay, yes, a Doppler shift of 2.2 megahertz, sorry, 0.2 megahertz. But mainly because the reflected frequency was greater than the transmitted frequency, this becomes as okay, a positive Doppler shift. Or you can mainly say, okay, that we subtract a smaller number from a bigger number, your balance is still going to be positive. You had $2,200 and you spent $2,000. You still have $200 left, right? Did that make sense? Did that make sense? Do you still have a positive bank balance? Any question, ladies?
No.
Whereas, okay, yes, on the other hand, if you say that the reflected frequency was lesser than the transmitted frequency. Now, what that is going to just, okay, become is a negative Doppler shift. And again, we can say it's okay here. You only had just, okay, $1,800 in your bank. But you still bought a pair of shoes that cost you $2,000. So what is it that, well, okay, the difference between us, okay, the amount of money that you had in the bank and the money that you spent was $200. But because you only had $1,800, but you spent $2,000, your bank balance is now going to be as okay, negative. So you have a negative Doppler shift. Where the positive Doppler shift mainly means we can say as okay that the distance between the source, which is your transducer, which is going to transmit at a frequency which we'll call the transmitter frequency, and reflector, which produces as okay a reflecting frequency. Now here as okay your reflector is going to be as okay the red blood cell is decreasing. So when as okay the distance between as okay two things decreases, what does that mean? That they are moving closer to one another, right?
Right.
Right. You're standing by the side of the street and you see a car coming towards you. Well, okay, you're not moving, you're just standing there. But it's okay, it's coming towards you. That is going to be as okay a positive Doppler shift between you and that car, or a bus or bicycle. It could be anything. Did that make sense? So maybe yes, okay, that distance between yes, okay, you as the transducer or source and that object now coming towards you is going to be considered as a positive Doppler shift. So for now, girls, just remember that distance between the red blood the transducer and the red blood cell, if that decreases, we will refer to that as a positive Doppler shift. Or we can say that the red blood cell is moving towards the transducer. Did you girls get that?
Yes.
Good. So the distance between, yes, okay, the source, which is your transducer, and the reflector, which is your going, in this case, as okay, going to be the red blood cell. is decreasing, that's what we will call a positive Doppler shift. Did you ladies get that? Whereas the opposite is going to just happen when we talk of a negative Doppler shift. So what is a negative Doppler shift? We can mainly say, that's going to be when the distance between, that's the same source, which fires out at a frequency of the transducer and the reflector is increasing. So when the distance between you and a car or a bike or a motorcycle or a bus or whatever you're looking at is increasing, that will mainly mean that, it is traveling away from you, right?
Right.
Okay, so a negative Doppler shift for now, girls, just remember this much. That will mainly mean that the red blood cell is traveling, or we refer to that as when the red blood cell or the reflector is traveling away from the transducer. So positive Doppler shift when the red blood cell approaches the transducer, negative Doppler shift when the red blood cells moves away from the transducer. Clear? Mathematically, how is that determined? When your transmitted frequency is lesser than the reflected frequency. Or you can say the reflected frequency is greater than the transmitted frequency. That will mainly mean that, that reflector is moving towards your transducer. So you have a positive Doppler shift. Whereas on the other hand, if the reflected frequency is lesser than the transmitted frequency, or you can say the transmitted frequency is greater than the reflected frequency, that will mainly mean that the reflector, or in this case, yes, your red blood cell is moving away from the transducer. Did you girls get that?
Yes.
Okay. Whereas if the two are equal, the transmitted frequency was 2 megahertz and the reflected frequency was 2 megahertz. That will mainly mean that, yes, your reflector is not moving. It's not moving away from you or from the transducer. It's not moving towards the transducer. Did you ladies get that?
Yes.
Okay. Any questions?
No.
Okay, Marissa, I don't expect you to have a question. Any of the new girls? Nope. Yes, ladies. Okay. So please, 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 what we call a Doppler frequency can also be referred to as a Doppler shift because it means it's just a shift in the frequency. Clear? Okay. But yes, okay, back to our submarines. The frequency at which they transmitted. And if they start getting reflections back, or reflecting frequency back at a higher frequency, what they mainly would assume is that this dude here is he is moving towards us. Now I don't know how they were able to communicate with him or say, well, listen, buddy, you're getting too close. We don't like you in our waters, so get the hell out of here. Okay. By if the frequency at which if the reflected frequency was lesser than the transmitted, they will mean say, well, well, it was a submarine, but probably we were detected by it and it didn't want to take up or mess around with us. So that's why I mean it's just quietly trying not to sail away. Right? But they have the same mechanisms for aeroplanes as well. Mainly just prevent just mid-air collisions between planes. Now even as you can say it's newer model of cars. Now you may have seen or you may have heard of it. That as in the side mirrors, there's that little blinking, the blind side mirror. What does that tell you? That as a car in your blind area or blind zone is approaching you. How does it detect that? Mainly because the distance between your car and that other car is decreasing. So it warns you as don't do a line shift because you may get hit by a car that is in your what they call a blind field. Okay, which you don't directly will be able to see in your mirror. So even there, yes, you have Doppler technology. Any questions so far? So for now, just remember positive Doppler shift. If the reflector, which in this case here is the red blood cell, moves towards the transducer. Negative Doppler shift, if the reflector, which is the red blood cell, moves away from the transducer. Clear? And zero Doppler shift. Well, for now, if your reflector does not move towards the transducer or away from the transducer. But what we will see later on is that, there are instances where that we have a blood flow. The blood is flowing, but you may still just to begin with just have a zero Doppler shift. So how do we actually end up dealing with that? That's going to be another thing. But does anybody have any questions about positive Doppler shift, negative Doppler shift? So the positive factor, the negative factor mainly is just determined by the direction, of the flow of blood towards transducer, away from transducer. Did all of you get that?
Yes.
Good. Let's see. Because now we can say it's okay. Your Doppler shift. Now, primarily mainly was going to be as okay, the difference between it's okay, your transmitter frequency. And we can say it's okay, transmitter frequency. From your vector frequency, reflector frequency. Now what we can say here is, okay, yes, we start off with, let's say it's okay, a transmitter frequency of 3 megahertz. Is that clear? Where we have, okay, as a reflector frequency of, let's say it's okay, 4.5 megahertz. Did you girls get that? So we can mainly say as, okay, now the Doppler shift here, as far as the numerical value is concerned, we can say it's okay, will be 1.5 megahertz. Right? Right, girls?
Right.
Good. Now my question is going to be, is it going to be positive or negative?
Positive.
Very good. It's going to be positive. So in this instance, yes, okay, we can mean says, okay, the difference between the two frequencies was just, okay, 1.5 megahertz. And we say, yes, okay, we had a positive Doppler shift. The positive mean is going to mean, yes, okay, that the flow of the red blood cell is towards the transducer. Let's say that, okay, yes, we use the same transducer with the same frequency. Of 3 megahertz. But let's say that in this case here, the reflector frequency is going to be as, okay, 3.2 megahertz. Now we can say as, okay, the Doppler shift in this case here is going to be the difference between these two here, which is going to be as, okay, 0.2 megahertz. Right? Right, girls?
Yes.
Good. Okay. Anybody beside Dr. Remus And tell me whether this is going to be a positive Doppler shift or negative Doppler shift.
Positive.
Positive. But what we mainly see here is, okay, as comparing as, okay, the two as, okay, examples. We could just say, okay, this is example A, this is example B. That, okay, as an example A, yes, okay, what is it that we have? We have a greater Doppler shift, right? Because the difference between the two frequencies came out as, okay, 1.5 megahertz. Compared to down here. Now, both of them are positive. Okay, the positive, yes, okay, me, yes, okay, then in this case, yes, okay. The red blood cell, yes, okay, is moving, yes, okay, towards the transducer. But yes, okay, in example B, what we mainly see is that, okay, as we have a lower Doppler shift. Because, as okay, the difference between the frequency was only as, okay, 0.2 megahertz. Did you girls get that? Did you girls get that?
Yes.
Right, okay. Now, what is it that this says, okay, 1.5 megahertz, which is going to be, okay, great Doppler shift. Or it's, okay, 0.2 megahertz, which is going to be, okay, a low Doppler shift. Is going to mean the direction is already said, well, okay, it's towards transducer. That's why it's, okay, in both cases, it was positive Doppler shifts. Why? Because your reflected frequency was greater than your transmitter frequency. The reflected frequency was greater than the transmitter frequency. But in example A, we can say, okay, the difference between the two frequencies was greater compared to, okay, what we have in example B, where the difference between the two frequencies was lesser. Which mainly mean that, okay, yes, here, the red blood cell is moving towards the transducer, or giving us, like, as a positive Doppler shift. But that greater Doppler shift value here mainly means that, okay, yes, we have a greater speed, which we could just, for instance, say as, okay, that it could be as, okay, as 15 centimeters per second. That was the speed at which the red blood cell was moving towards the transducer. The towards factor gave us a positive. Okay, where, okay, as the frequency here could just be as, okay, translated into speed. Whereas here, mainly as, okay, due to the lower Doppler shift because of the lower difference between the two frequencies. Mainly will mean, well, okay, it's still positive, so that means, okay, the red blood cell travel towards the transducer. But as, okay, here we mean it says, okay, that 0.2 megahertz. Can you get just, okay, assume that, okay, that becomes 2 centimeters per second, which means, okay, we mean that, okay, it's going to be, as, okay, at a lower speed. But still, it's, okay, at a lower speed, traveling slower towards the transducer. Did you ladies get that?
Yes.
Okay, so pretty much, okay, yes, with help of, yes, okay, whether you have a greater difference or a lower difference between, yes, okay, the two frequencies. Okay, the system will be able to determine, is this red blood cell here, is okay, zoom fast towards us or even away from us, or is it traveling slow? The away factor would just have been as okay, we just had, let's say, as okay, shifted the frequencies and say, well, okay, what if our reflector frequency was okay as 3 megahertz, where okay as the transmitter frequency, for instance, had been 4.5 megahertz. We would actually, okay, in this case, is okay, end up with a negative Doppler shift because the transmitter frequency was lesser than the, the reflector frequency was lesser than the transmitter frequency. But yes, okay, the difference was still yes, okay, 1.5 megahertz. We just roughly, okay. We could just okay assume that okay 1.5 megahertz means okay we're indicating yes okay that the speed is 15 centimeters per second. So yes, okay, the blood could still yes okay flow at a speed of 15 centimeters per second, but away from the transducer. Clear? Okay. So the positive factor, the negative factor of your Doppler shift is based upon the direction, where okay as the physical yes okay the numerical value of your velocity is based on the numerical difference, or that's okay the numerical value of your Doppler shift. Did that make sense? So if we say it's okay a negative Doppler shift of 15 centimeters per second, the negative just means away from transducer, moving away from the transducer at a speed of 15 centimeters per second. Whereas if we say it's okay a positive Doppler shift of 15 centimeters per second, the positive meaning is okay Doppler shift just means that the red blood cell is moving towards the transducer. At what speed? 15 centimeters. How do we get that? Mainly because okay, we had a great Doppler shift. A great Doppler shift is going to be as okay, a great difference between the two frequencies that are being utilized to calculate or determine the Doppler shift, which is actually going to be primarily a Doppler frequency. Right. Okay. What determines whether it's positive or negative? It determines which of the two frequencies were greater than the other. Any questions? Okay, girls. How is Doppler going so far?
It's going.
Huh?
It's going.
Okay. Is the reflector frequency greater than the transmitter frequency?
Yes.
Okay. That means that okay is positive.
Yes, it is.
Okay. Let's hope it stays that. Okay, there. Okay, girls. Okay. Just take a short 10 minutes break. Please, that's okay. Read on. That's okay because that's okay. The first page. And please make sure that you, that's okay, get on top of positive and negative at least. Okay. And we will then, yes, okay, start talking of, okay, something that we'll call, yes, okay, the Doppler equation when we come back. Okay. Okay, girls.
Okay.
Okay, girls, welcome back. Okay, now does anybody have any questions at this moment? No?
No.
Okay. Okay, girls. Now, just one thing before we, yes, okay, start talking of the Doppler equation, and that is why is Doppler shift shown as a velocity and not the frequency? Just look at this. I may say, well, okay, you have a Doppler shift of 2 megahertz. This doesn't tell you much. Right, okay. It may just tell you, yes, okay, that, okay, yes, the difference between the transmitted frequency and we can say, okay, reflected frequency was 2 megahertz. Okay. But you don't know whether, yes, okay, this is going to mean, yes, okay, a high velocity or a low velocity. So that is mainly, yes, okay, why your system primarily, yes, okay, will show, yes, okay, your Doppler shifts as a velocity, which is going to be, yes, okay, in any unit of distance by unit of time. Although, yes, okay, what the system receives of info to calculate a Doppler shift frequency is going to be, it's okay, the difference between the two frequencies. But we use these differences here to calculate the speed, XYZ number of centimeters per second. And as we said, all depended upon which was greater and smaller, be a negative Doppler shift, which was lesser and greater will be a positive Doppler shift. Right, okay, which means your mean towards transducer, away from transducer. Okay, now what you may see on the system, oh, sorry. Oh, let's see, it's okay, your screen. Let's see that's another screen. We can say it's okay, this was your display. Clear? You have your B mode image here. Clear? Where, okay, as you have structures, you can even say it's okay. You will have a blood vessel in which it's okay, the blood is flowing. Now, one way in which, okay, yes, your Doppler shift can be as okay shown is going to be as okay, like a graph like this. Okay, this, we talk about this later, but this is going to be as okay, what we call a spectral Doppler. Where you actually is okay, may see is okay, we can say it's okay, a graph. That goes like this. Now you okay. You will here see is okay, this will say 0. So this line here is okay, may indicate 0. Ideally, yes, okay, unless and until we, yes, okay, don't play around with it. Oh, yes, okay. Change some settings on the system. Anything about the baseline or the 0 line is going to be positive Doppler shift. Whereas below the baseline is going to be, yes, okay, negative Doppler shift. So in this case, yes, okay, we have a positive Doppler shift. But then it's okay, here you will have different velocities. We can say, okay, 10 centimeters per second, 20 centimeters per second, 30 centimeters per second, 40 centimeters per second, 50 centimeters per second. So on this side here, it's okay, it's going to be as okay. The readings is going to be as okay in centimeters or meters per second, which is mean as okay, just going to be as okay, your speed. It all dependent upon as okay, whether you had a graph on this side of your 0 line or on this side of your 0 line will determine as okay, whether you had a positive Doppler shift or whether you had, let's see, it's okay, yeah, negative Doppler shift. Because if your graph had been like this, now it had been okay as a negative Doppler shift. Where again, yes, okay, we'll just see here that it says, okay, minus 10, minus 20, minus 30, minus 40, minus 50 centimeters. Now, some systems may even over here, so okay, give you other values as well, which is just going to be as okay, your frequencies in hertz. Or kilohertz or whatever. Which means it's okay, we just indicate it's okay, the Doppler shift frequency expressed in a unit frequency. But these numbers here, we really can't use them for much because they're going to say, well, okay, this is going to be as okay, the difference between the two frequencies, which were okay as you're transmitted, and your effective frequency. Did that make sense? But the actual value is okay, that's going to is okay, revert for us to is okay, look at to determine is okay, the speed of blood, whether it's high or low, is going to be is okay, what we find on this side here of the spectrum. Mainly because it's okay, you will not be able to is okay, get much out of them, okay, a Doppler shift of okay, as 20 hertz. What does that mean? Is that clear? But if I say that's okay, 15 centimeters per square second, you will say, okay, yes, that's the speed. Did that make sense? Right. Okay. Any questions? Any question, ladies?
No. Okay, girls. Now you may in your book see an equation that says on page 306. Does everybody have their books? Yes.
Okay. And if you go on page 306, and you see it's okay, the heading to that is the Doppler equation. Now I may, or we may know that whenever some of you see the word equation, you think of math, right? Right, ladies? Okay, listen. This Doppler equation here is okay. Don't have to remember the Doppler equation. Okay? Is that clear? So you don't have to remember the Doppler equation by heart. But that's about it. What is going to be important is, yes, okay, because the Doppler equation is to multiply by, we can say, okay, velocity of blood multiply by, yes, okay, the transducer's frequency multiply by the cosine theta divided by propagation speed. That was your Doppler equation, right? Here, I covered it up in my book.
This was the Doppler equation, right? Right, girls?
Yes.
Okay. Now, the main thing, ladies, that is going to be important is that you know the relationships between, yes, okay, what we call the Doppler shift. We also know that we also call this fellow here, yes, okay, the Doppler frequency. Just so you remember, okay, yes, what was that? That was mainly, yes, okay, just the difference between, yes, okay, the difference between the transmitted frequency separated subtracted from the reflected frequency. That gives us, okay, as the Doppler shift, or what we call the Doppler frequency. Right? Right, girls?
Yes.
Good. Now, what the system will be doing based on these frequencies here. Yes, okay. Actually, it's okay. And with help of, okay, as the velocity of the blood. The transducer's frequency. And something is okay, which, okay, it's not that complicated, but it's okay, we'll talk about it. It's going to be, okay, the cosine theta value of different angles between our beam and the direction in which the blood flows. Well, yes, okay, give us a Doppler shift. But what we mainly, as okay, we'll be discussing is going to be, as okay, the relation between Doppler shift, or what we also call Doppler frequency, to the relation between Doppler shift and or Doppler frequency and the velocity of blood. The relationship between Doppler shift and frequency, Doppler frequency, to the transducer's frequency. Now, ladies, when we said transducer's frequency, we already said that, okay, that was going to be as, okay, the transmitted frequency. Right? But its relationship to the Doppler shift or Doppler frequency is important. Likewise, is going to be as, okay, the relationship of your Doppler shift. All Doppler frequencies relationship to the cosine theta value of angle is going to be important. But what you can mainly see here is, okay, all these three factors here. Whether it was the velocity of blood, whether it was the transducer's frequency or transmitted frequency, or whether it was going to be as, okay, the cosine theta or as, okay, the cosine theta value of the angle are all, yes, okay, numerators of your Doppler equation, right? So what did that tell you? That all these three fellows here are going to be directly proportional to your Doppler shift. Did that make it simple? Yes, girls,
Yes.
Yes.
because you can mainly say, okay, if any of these numbers are okay, if all of them are greater, what is it that we will be getting? A greater Doppler shift. Okay. The one factor that we're not going to be discussing here is going to be okay, propagation speed. So, well, okay, you can mainly say, okay, Hakuna Matata that one. And what we briefly mentioned is, okay, why in the to multiply all this here by 2. What is this 2 here for? Yeah. So yes, okay, our simple way of, okay, yes, or we may be doing is, okay, or what you can be asked questions about is to calculate the Doppler shift or the Doppler frequency. But for that, you need, okay, as a transmitted frequency and a reflected frequency. And you may just, okay, just subtract those two from one another. Where you can get a positive value or a negative value. The positive and negative value is mainly as, okay, just going to be as, okay, a factor here. Because we mainly said that, okay, yes, velocity was mainly as, okay, just a speed in direction. So the direction is going to is okay be important here. But how is it that the system actually is okay to be able to determine the direction? Is going to be the help of this. Where here we can mainly say, okay, a great speed will give you a great Doppler shift. A low speed will give you okay a low Doppler shift. Whereas the positive and negative mainly was just towards transducer or away from transducer. Right. You can also say as okay, great transducer frequency. If you use a transducer with a high frequency, it's going to give us okay as a great Doppler shift. Whereas on the other hand, if you use a low frequency transducer, it's going to give us a low Doppler shift. Okay. And what you girls just okay will come across or what we will see is that okay, as a high Doppler shift is good, but then too much good becomes bad. Okay. Okay, girls.
Okay.
Good is good, but then too much good may become bad. So that's why we say it's okay. That we can reduce the Doppler, or we can reduce the transducer's frequency, meaning it's okay to reduce the Doppler shift to make it come back from bad back to normal good. Okay. But it's okay. Just here you can mean it says okay, all these 3 factors here. Whether it's the velocity of blood, or we can say it's okay, the speed of blood. The faster the blood is moving, and way too worse is not a question here. It's going to just okay give you a greater or lesser Doppler shift. The higher or lesser the transducer frequency is, it's going to give you okay a higher or lesser Doppler shift. And the greater the cosine theta value of the angle. Now let's just, okay, elaborate the angle here. Because it's, okay, between the beam. What beam? Of our ultrasound. And direction of blood flow. So that actually, that's, okay, is going to be an angle between the direction of your ultrasound beam and the direction in which the blood flow. And that angle will have, okay, as its own cosine theta value. And the greater the cosine theta value is, the greater will be the Doppler shift. Okay, so all these three here, yes, okay, are directly proportional to your Doppler shift. Any questions? Why? Because mainly, yes, okay, they were all these three here were the numerators in your equation, right? By now you should know, okay. I shouldn't say what you should know. Well, that's okay. Any equation or any is okay thing that we have been calculating so far, you will actually have come across that, okay, as whatever factor you calculate is directly proportional to the numerator, inversely proportional to the denominator. So what does the denominator mean? That you divide the upper numerator by that number, right? So the greater your numerator, the greater will be the factor. Here your factor is the Doppler shift. What was your Doppler shift? The shift in the frequencies. Right, okay. How did we calculate that? How did we calculate that? The difference between the two frequencies, transmit and reflected frequency. Clear? Now goes. First of all, we can say it's okay. Doppler shift or Doppler frequency. Well, okay, yes. Why the two? What the blue does the two? Or why is the two in the equation? Now just keep in mind, it's okay, girl, this number here is fixed. It's not something that we can say, okay, if you want to, yes, okay, can we make it 4? Or if you want it, can we make it 1? If you want it, can we make it 6? If you want it, can we make it, yes, okay, a half? No. This is fixed. Okay? So, yes, okay. All these and all these here, yes, okay, are out of question. And the reason that they put 2 in the equation is mainly because, okay, your Doppler shift mainly is okay, is being calculated by using 2 frequencies. What were those frequencies? Your transmitter frequency and your reflector frequency. Did that make sense?
Yes.
Right, okay. So that's the reason why it's okay. We have 2 in the equation. So that's your 2. 2 is 2. 2 is gone. Or we can say, it's okay, 2 is being discussed. So there's not much. Sorry. There's not much of a discussion about that. Now, the next was, you can say, okay, the Doppler shift. If somebody don't like the word Doppler shift, just remember that, okay, we can also call it, yes, okay, a Doppler frequency. But the reason that they call it a Doppler shift is mainly because, okay, the Doppler shift actually is was a shift in the frequency, a change in the frequency. Right? Clear? Okay.
Yeah.
And we can now see it's okay. Now the second factor that we had in our Doppler equation was the velocity of blood. Velocity of speed, what the hell? So, velocity of blood. Okay. Where, okay, so what was the velocity? That was mean it's okay, just a 2-factor thing, which was determined by the speed, which is going to be expressed by any unit of distance by unit of time. Other factor was direction of motion. Or in this case here, we can say flow. Because, okay, blood was a liquid. Okay, where this could be expressed as either positive or negative. But what I said was that, okay, yes, these two here are going to be directly proportional. Now, I think I already, yes, okay, displayed that here. Did you see that one? Or do you remember this one? Yes, ladies.
Yeah.
Okay, Shaq, remember it. Okay, now please, 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 don't come back to me and say, Mike, 1.5 megahertz Doppler shift is not 15 centimeters per second. It's 15 meters per second, or it's 27 meters per second, or whatever. This was just yes, okay. 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 But what we mainly is okay, just could say or could just say was that the greater the Doppler shift will mainly mean that, okay, as the blood is flowing at a greater speed. Whereas if we say, yes, okay, the lower the Doppler shift, a Doppler frequency mainly will mean that, okay, the blood was flowing at a lower speed. But as far as the speed was concerned, yes, okay, it could be a high speed, which would be positive. It could be a high speed, which was negative. Likewise, that's okay, you could have a low speed, which was positive. And you could have a low speed, which was negative. Because the positive and negative only is okay indicates the direction of the flow of the blood. Which was, is it towards the transducer? Is it away from transducer? Clear? So for remaining is okay, says okay, here is okay. In a great Doppler shift, that will mainly mean that okay, as that there was a great difference between, yes, okay, the two frequencies that we used, which was okay as the transmitted frequency and the reflected frequency. If we had a great difference between those two frequencies, what the system mainly is okay, will figure out from that is that the blood is moving at a great speed. Now, all dependent upon which of these two frequencies here was greater and which was lower would determine whether it was going to be as okay a positive frequency or a positive Doppler shift or a negative Doppler shift. Clear. So we could have a speed which, for let's say, if he says okay was high, let's say it's okay 100 centimeters per second and 100 centimeters per second. Both the Romanians, okay, just indicate along in this instance, okay, that we had a great difference between the two frequencies. Okay, let's say that, okay, yes, the difference between these two frequencies was, let's say, okay, just in kilohertz. They're all dependent upon us, okay, which one was greater. And which one was lesser. Would make it a negative Doppler shift. Or which one was lesser and which one was greater, will make it a positive Doppler shift. Okay. Where we mainly will say here is, okay, the blood is moving towards the transducer at a speed of 100 centimeters per second. Now, towards the transducer will become positive. The speed is 100 centimeters per second. But it could still move at 100 centimeters per second and be negative because it will move away from the transducer. How would the system figure that out? Because, okay, the reflected frequency was lesser than the transmitted frequency. Did you girls get that? Whereas, okay, yes, if you said that we have a low speed, which means that, okay, we have a low Doppler shift, which means that, okay, there will be, yes, okay, a small difference between, yes, okay, our two frequencies, which is still going to be, yes, okay, the transmitter frequency and our reflected frequency. Let's just say that in this case, yes, okay, we only had a difference of 1 kilohertz. The difference was 1 kilohertz. Now let's just assume that the system is okay, calculate that as a speed. Or let's say it's okay, 10 centimeters per second. But how does it get that? Meaning because it's okay, we have a lesser difference between the two frequencies. Where, okay, yes, it can still be positive. Now, why would make it positive? Still, yes, okay, if the reflected frequency was greater than the transmitted frequency. But the difference between the two was lesser than, okay, yes, in this instance here. That we only had a difference of, let's say, 1 kilohertz. Which the system will calculate, okay, at this blood moves at a speed of 10 centimeters per second. All depending upon which is lowest and which is greatest of the two frequencies, it will see it's okay, it is positive. Yeah, positive, we know means, okay, yes, moving at a speed of, or moving towards the transducer. But we can still have, okay, yes, a low difference, a small difference between the two frequencies. Okay, and have a negative Doppler shift. And that's mainly as okay when the transmitted frequency was greater than the reflected frequency. Where the negative factor just the chart as okay tells the system, well, okay, the red blood cells is moving away from the transducer. Did you get that? It's moving away from the transducer, whereas okay, positive towards the transducer. But it's okay, here it is moving slowly towards the transducer or away from the transducer compared to up here, where it's moving fast towards or away. So the greater the speed of blood, well, okay, yes, the greater will be the Doppler shift. That positive and negative mainly only comes into effect because we talk about is okay, the direction. But we can have a great positive Doppler shift. We can have a great negative Doppler shift. We can have a low positive Doppler shift. We can have a low positive Doppler shift or low negative Doppler shift. Sorry. Did you ladies get that? So what the Doppler equation, which means is okay, something that the system does. Is just okay based on just okay the difference between the two frequencies determines the speed. And based on which of those two frequencies was greater and which of those two frequencies were lower, determines is it positive, positive? Is it negative? Negative. Did you girls get that?
Yes.
Okay, Marissa. Some of the new girls. Anybody have any questions? Is there anybody who is still confused about positive versus negative? No? Okay. Anybody who is in doubt about low velocity or low speed versus high speed? No? Okay, ladies. Now just the next thing. And that is, okay, yes. The Doppler shift. Sorry. The Doppler shift. Or what we also call is, okay, the Doppler frequency. And its relation to the transducer's frequency. It goes. And what we mainly, as okay, said earlier, is that they will be directly proportional. Okay. Now we can just say, okay, say, let's take, say that we, okay, let's take an example of, okay, as two transducers. With, let's say, it's okay, two different frequencies. We can say as, okay, we have a 4 megahertz transducer. And we say, okay, as a 8 megahertz transducer. Well, I just, okay. Where we can say is, okay, this one here is the transducer with a low frequency. Whereas, okay, yes, this one here is the transducer with a great frequency. Right? Right, ladies?
Yes.
Good. Now, what this low frequency transducer here is okay may produce is going to be as okay a low Doppler shift. Let's just say that okay, as our low Doppler shift in this case here was 2 kilohertz. Now we said that Doppler shift is directly proportional to the transducer's frequency. So if you double, I will use a transducer with a double frequency, which will be 8 megahertz. Okay, yes, it's directly proportional because, okay, the greater the transducer's frequency, the greater will be the Doppler shift. So we have, okay, as a greater Doppler shift frequency. Which means in this case will be that, okay, yes, it doubled. So yes, okay, our Doppler shift frequency will be 4 kilohertz. Is that clear? So right now, girls, just keep that, okay, yes, this relationship here. And you just, yes, okay, have to remember the relationship. It's very important. Because, okay, that's going to become, yes, okay, handy at some point. Where we may see, yes, okay, that too high of a Doppler shift actually is okay, is due to, yes, okay, too high of a transducer frequency. Where good was good, but then too much good is bad. Because in that instance, in that case, that's okay, we get too high of a frequency. I'm sorry, too high of a Doppler shift. That actually is okay, is going to, is okay, cause it to be as okay, a bad Doppler shift. So how do we just okay make this bad good again? We can mean it says, okay, well, let's just okay, let's take it down to a lower frequency. Or let's say even if this one here is okay, was bad, we could just say, okay, let's just use a transducer with a lower frequency. Is that clear? Okay. Here, yes, okay. Now in this case, we can say, okay, this was the transducer's frequency. We could have got, okay, let's say, yes, okay. If the reflector frequency, for instance, was 4 point, let's say, sorry. 4.02 megahertz, if that was the reflected frequency. We still had a Doppler shift of, okay, yes, 2 kilohertz. But whereas, okay, here your reflected frequency was the greater one. And the transmitter frequency was the lower one. So we got a Doppler shift of 2 kilohertz. Where, okay, It could also, okay, sorry, that's true. Let's see. Let's take this guy. If our reflector frequency was 3.8 kilo megahertz, we still had a frequency or Doppler shift of 2 kilohertz. Oh yes, okay. In this instance, it's okay if you are going to have a negative Doppler shift because the reflector frequency was lower. But we can say, okay, it will still be as okay a low Doppler shift. There, okay, yes, if we used the same instance, okay, the high frequency transducer, yes, okay, the Doppler shift would be 8.04. Or it could be as okay, 7.06. As okay as our reflective frequencies. Best sense here is okay, we had a greater reflective frequency than the transmitter frequency. It was going to become a positive. Where here's okay, the reflective frequency was lesser than the transmitter frequency. Yes, okay, it would be negative. But here's okay, in both instances, okay, we had a difference of 4 kilohertz between the transmitted and the reflected. The transmitted and the reflected. Mainly because, okay, we use a high frequency transducer. Okay, and please, 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 ladies, it is a transducer's frequency, not your PRF. Okay? Okay, girls?
Okay.
It is your transducer's frequency, it's not your frame rate that we are talking about. Although, yes, okay, later in Doppler, yes, okay, we may talk of PRF. But for now, yes, just remember this relationship that, okay, yes, if we use a transducer with a lower frequency, we will have a lower Doppler shift. If we use a transducer with a greater frequency, we will have a greater Doppler shift. Because these two here are directly proportional to one another. Okay. Although in both instances, okay, the blood may be flowing at the same speed. Okay. That's probably okay, one of the factors in your Doppler equation that you are not able to control. Okay. It's not you who controls how fast or slow the blood of the patient flows. Practically. Okay. But that's okay. Can you increase the blood flow? Or can you increase the speed at which the blood flows? Let's go. Do you want me to increase the speed at which your blood flows? Right here and now. I can do that. You may not like it, but okay. It always is worth a try. Because girls, I'm going to finish off with chapter 19 here. You read it by yourself, and your quiz is on Friday. Now, some of you may start getting tachycardia. Okay, yes, your blood is going to be flowing at a faster speed, right? Okay, but practically, yes, okay, we are not able to, yes, okay, manipulate with the speed at which the blood flows. So, yes, okay, just keep that one in mind because, yes, okay, there are going to be questions in your exercise. Where you look at, okay, yes, they both talk about Doppler shift. They both talk about so and so on, but how is it that, okay, in one case, yes, okay, it has a difference, it's the same, and in another case, is different. That's because in one case, they ask about, yes, okay, the velocity of blood. And in one case, they ask about the transducer's frequency. So that's okay. If you increase the frequency of the transducer, that's okay. That's going to increase your Doppler shift. But the velocity of blood is not going to increase just because you use a different transducer. You may just get a higher Doppler shift reading. Did that make sense? Okay. But okay, at that higher Doppler shift reading, okay, yes, maybe good. Maybe too much good becomes bad. So that too much good become bad, yes, okay, we will talk about that fellow in a whole separate class. That's going to be 1 day class for that. Too much good is bad. Okay? Okay. So you remain, yes, okay. You will be asked about, okay, which of these two transducers here will have the greatest Doppler shift. It's straightforward. If you just remember the relationship, the Doppler shift is directly proportional to frequency. You just have to look for the one with the highest frequency. That will have the highest Doppler shift. The one with the lower frequency, yes, okay, lower frequency is going to give you a lower Doppler shift. Even though it's okay, you scan the same patient. Okay, as long as his blood is flowing at the same speed. Did that make sense? Did that make sense, ladies?
So it's only directly related if the blood is flowing at the same speed?
Your frequency, yes.
Yes, okay.
Okay, but if yes, okay, if you had a patient who just okay has had an it's okay just did exercise versus a patient who comes in at rest. Okay, of course that's okay. Their blood is going to be flowing at different speeds. But it's okay if you have a patient whose blood is flowing at a greater speed, you will have a greater Doppler shift. Versus a patient whose blood is flowing at a lower speed, you will have a lower Doppler shift. Or, as we said yesterday, in which part of the vessel is it that the blood is going to be flowing at a greater speed time in the same patient? Did you guys get the diagrams I sent you? Everybody should have got that email.
Yes, I got them.
You got them. Okay. Anybody who didn't get an email from me yesterday? Okay. There are 11 girls who don't know whether they got an email or not.
I got
Okay.
it.
I got it.
Okay.
I got it.
Okay. Thank you. And for those of you who still don't know whether you got it or not, it should be in your email box. If you didn't get it, then send an email saying I didn't get it. So my question is still unanswered. Same patient, but in which part of his blood vessel will you have a higher velocity?
Pulse and pre-stenotic.
Huh?
Pulse and pre-stenotic.
Pre-stenotic, okay.
Would it be during stenosis?
At the stenosis, right? Right. So if you scan at the level of the stenosis, what is it that you will find there? A high Doppler shift. How is that high Doppler shift going to be displayed as a high velocity? That high velocity, yes, okay, will indicate that you have, okay, some issues. It also gives us, okay, something else, which is going to be turbulence. Right? So yes, okay, how to, yes, okay, look out for those factors and differentiate between the two. Is this as a high speed due to, yes, okay, a narrowing? Or is it just, okay, high speed with turbulence? Is mainly as, okay, things that we will come up as, okay, try to, as, okay, sort out as we proceed through this chapter here. Now, girls, just take your lunch break. But before coming back from lunch, please go back to chapter number 6. You see, you can't escape chapter 6, okay? Okay, ladies? And yes, okay, look at what we call the angles. Right angles, oblique angles. And oblique angles, we had acute angles and obtuse angles, right? And if some of you, yes, okay, didn't get it, then let me just repeat myself. Because I said back then that a 90-degree angle or a right angle was ideal for diagnostic imaging, where your goal was to get, yes, okay, an image. Right? Now, a 90-degree angle is not ideal for Doppler. Because what I said in the beginning of today's class was Doppler was not the goal of a Doppler exam, was not to get a picture. You want a picture, of course, so you know, yes, okay, where you're recording. Okay. But the main goal was to, yes, okay, record the velocity of the blood. So you may see that, okay, as a 90-degree angle is going to be a non-ideal angle of Doppler. And how and why and we will talk about that when we get back to, oh yes, okay, when we return back after lunch. So would it be fair that I see you girls at 12 45.
Okay.
Okay, ladies, then enjoy your meal. Yes, ladies, welcome back. Um, Now, before I kickstart the next topic, any questions? Yes, ladies, any questions? So far you're getting the Doppler thing? Okay, girls. Now the next thing that we were talking about, let's do it this way. Or we can actually see that, okay, yes, the Doppler shift is directly proportional to the cosine theta value of the angle. Now, first of all, ladies, when we say angle, what angle? Okay, which angle are we talking about? Okay. So that means, okay, going to be, we can say, okay, the angle between the beam. Now, when we say beam, I hope everybody will know what that means. Ultrasound beam, right? And you can say it's okay, the direction of the blood flow. Did you girls get that? So we can say that, okay, yes, if we had a blood vessel, this was a blood vessel, right? Right, girls?
Yes.
Okay, so you think this is a blood vessel, my dear? Yes, Dr. Marissa. Do you think this is a blood vessel? Marissa, was that you who said yes? I guess, okay, not, okay. And okay, yes, mainly yes, okay, let's just take yes, okay, one direction. And we say yes, okay, if this, in this instance, yes, okay, was the direction in which the blood was flowing, right? And now we're going to talk about, yes, okay, the angle between the beam. So if this here was the transducer and it sends out a beam like this, or you can say, yes, okay, the direction of the blood in this case is okay, is towards the transducer. But here we mainly, yes, okay, have, in this instance, yes, okay, our angle is going to be a 0-degree angle. Is that clear? So we actually, that's okay, have a 0-degree angle between the ultrasound beam and the direction in which the blood is flowing. Did you guys get that? Okay. Now, there can be, yes, okay, we can also have a 1-degree angle, a 2-degree angle, a 3-degree angle, 4 degrees, so on, so on, so on, so on. But we're not going to go into, yes, okay, each individual angle. We can just say that, for instance, if this here was our transducer, now if this was okay, yes, the direction in which the beam was forward traveling, we may say that okay, yes, this here may be yes, okay, 30-degree angle. Okay, let's just write that in. So we have a 30-degree angle. Is that clear? Whereas, okay, if you went a little bit more like this, oh, we can probably check this a little bit down. A little more accurate of authority. It can be something like this. But here we see it's okay that this was going to be a 30-degree angle. Between what? I mean, it's okay because you say, okay, sorry. If that, for instance, okay, hits down here. Okay, so this would be a 30-degree angle. Here, this was a 0-degree angle. Then we go a little bit further. And if we say this, or we can just say that this would be as okay a 60-degree angle. Between what? Between as okay the direction of the beam and the ultrasound and the direction of the blood flow. So this would have been as okay a 60-degree angle. Did you ladies get that? Now the next one that we can take is, what if we went like this? Now here you can mainly say that, okay, yes, we actually made a 90-degree angle between the beam and the direction of the blood flow. Did you girls get that? Next, if we go here. Well, we mainly will say that, okay, as this is going to be as okay an 120-degree angle. What will be a 120-degree angle in this case here? This one. Because it was okay, yes, an angle between the beam and the direction of the blood flow. Right? The next one. Would be as okay an angle of 150 degrees. What? This angle here roughly would be as okay 150 degrees. And last but not the least, oops, sorry. If we say that we okay a scan from here. In relation to the blood vessel, then this was going to be as okay 180 degrees. Between what? Between the beam and the direction of the blood flow. Because this here is 180 degrees. Did you girls get that?
Yes.
Right, okay. Okay. Does that mean that you can't scan from 70 degrees, 80 degrees, 50 degrees, 40 degrees, 20 degrees, 10 degrees? 100 degrees, 110 degrees, 130 degrees, 40 degrees, 160 degrees, 170 degrees? Of course you can, but we're not going to go into just, okay, all those values. Not to talk about, okay, what about a 1 angle or 5 angle, 10 degree, 12 degree, 15 degree, 27 degree, for instance. Okay. Now, each of those angles or individual angles will have their own cosine theta values. But we're just going to make it simple here. So, ladies, the cosine theta value of a 0 degree angle, because that's mainly a circuit what we are talking about, right? Right, okay. And what was that cosine theta angle? Oh, okay. Or cosine theta value of the angle. Which angle? The angle between is okay, the ultrasound beam and the direction of the blood flow. So yes, okay, your beam, 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 and the direction of blood flow makes certain angles. And those angles have their own cosine theta values. So those are mainly as okay, what we will actually as okay be filling into the equation now. So the cosine theta value of a 0 degree angle is 1. Is that clear? Did you girls get that?
Yes.
Now, who made up this number? I didn't make it up. Okay, people who as okay do geometry as a major or whatever. Okay, they may have those as okay scientific calculators and blah blah blah. It's okay when they want. It's okay. Put the cosine as okay. Type in an angle number. Any of these numbers as a cosine, it will convert it to 1 if it was a 0 degree angle. Clear? Okay, so these numbers are not numbers that I made up. These are numbers that made it pretty much okay as are going to be predetermined standard numbers. Clear? So the cosine, okay, the cosine theta value of a 0 degree angle is 1. The cosine theta value of a 30 degree angle is going to be as okay 0.85. No, sorry, 87, sorry. So 0.87. Did you girls get that? The cosine theta value of a 60 degree angle is 5 or is 0.5. Or we can say 0.5 is mainly as okay, just the CF, same as saying half. Did you girls get that? Now, ladies, when we went for our break, or before we went for our break, I told you that a 90 degree angle was not an ideal angle for Doppler. A 90 degree angle now between what? Between, yes, okay, the ultrasound. Oh, shit. Sorry, those. Between, yes, okay, the ultrasound beam and the direction of the blood flow, because you say, yes, okay, if the blood flows like this and our beam goes like this is a right angle, or this, there's no doubt about it, this is a 90-degree angle between the two, right? Now, why is that not going to be ideal for Doppler? Because the cosine theta value of a 90-degree is 0. Now, let me just take you girls, yes, okay, to the Doppler shift equation. Where we mainly said, okay, that's 2 multiplied by a velocity of blood multiplied by, yes, okay, the transducer's frequency multiplied by, okay, that's the cosine theta value of an angle, right? And that makes this, okay, it's divided by the propagation speed. But even if we said, okay, yes, the blood had a velocity of, let's say, 20 centimeters per second. We had a, let's say, it's okay, transducer frequency of, let's say, it's okay, 4 megahertz. Right? Okay, so you say, okay, this. Okay, right now our Doppler shift is 40. Multiplied by 4 becomes just, okay, 160. But if we say it's okay, a cosine theta value of 0, the whole equation becomes multiplied by 0, and that will mean that we end up with a Doppler shift of 0. Which mainly as okay may give us okay as the impression of as that there's no blood flow. Did that make sense? Any big number, you can take the biggest number on the earth and multiply by 0. What do you get?
0.
0. So here is okay. If the value of the cosine theta angle is 0, your whole equation gets multiplied by 0 and your Doppler shift comes out at 0, right? Okay. So what you want to avoid is to have a 90-degree angle between the beam and the direction of your blood flow. Because that's going to just, okay, indicate, yes, okay, yes, you have a Doppler shift of 0. Did that make sense? So when I once, okay, yes, upon a time, said that, okay, yes, a 90-degree angle is ideal for diagnostic imaging, where your goal is to, yes, okay, create an image, but not ideal for Doppler. That's why. Did that make sense? Okay, girls. So here, yes, okay, you do not want a 90-degree angle. And you say, well, okay, this is the transducer. This is the blood vessel. Well, okay, yes, we can always talk of, okay, yes, later on, how, yes, okay, may practically, yes, okay, change the angle of the beam. Because we will be able to, yes, okay, control that. Okay? But is there anybody who is in doubt why a 90-degree angle is not ideal for Doppler? Because the cosine theta value of a 90-degree angle is 0 when that is being put into the equation, the Doppler shift becomes 0. Is that clear, my girls? Okay. Now, it's not really that complicated because the cosine theta value of your 120 degrees is just going to be as okay 0.5 as well. But as okay here is a little different. Minus 0.5. Is that clear? Now you should already as okay be able to see as okay, guess what this minus here will do. It will cause your Doppler shift to become negative. Why negative? Because you're scanning from up here, for instance, and the blood is flowing. Yes, okay, you can say it's like away from the transducer. Your transducer is here and the blood is flowing in this direction. That's why it's okay, all these values here. Were positive. Why? Because you're scanning from here, you're scanning from here, you're scanning from here. And okay, yes, the blood flows in this direction. Clear? So if 120 is just the same cosine theta value as 60, just being minus, then you can say, well, okay, yes, the cosine theta value of 150 degrees is going to be as okay 8.70 or 0.87 negative. Did that make sense? Which mainly is okay, just brings us left with the question, when what about 190? All right, 180 degrees. Angle between the ultrasound beam and the direction of your ultrasound, or of the direction of the flow of blood. Well, okay, the cosine theta value of 180 is still going to be 1, but minus 1. Did you ladies get that? So what does the mining? It's going to be a negative Doppler shift because, okay, this is where you're scanning from. And you can say, okay, the direction in which the blood is flowing is away from the transducer, away from the transducer, away from the transducer. Because in this instance, okay, we said, okay, it is flowing in this way. Whereas if you had scanned from these angles over here, or we can say, okay, a beam was steered in this angle here. If the blood was flowing in this direction, these were going to be positive Doppler shifts. And the 90, bad, 0. Did you girls get that? Okay. So it's not going to be the number of the degree. It's not going to be the number of the angle of the degree that you will put in the equation. But the cosine theta value of each of those individual angles. Is that clear? Now, ladies, so some of you may be asking, so do we need to memorize the cosine theta values of these angles here? What do you think? No. That's contagious, my dear. Okay. The point is that we mainly as okay, just will say. Okay, get out. Okay, that this one here, which is a 0-degree angle, or this one here, which was a 100-degree angle. These are the two only angles where we mainly can say it's okay that the measured velocity equals to the actual velocity. Is that clear? Mainly because, okay, we multiply, yes, okay, all of the other factors by 1. It can be 1, or it can be, it's okay, -1. The -1 is going to just make it, okay, it's because it's okay, negative Doppler shift. Right? Whereas, okay, as if we take any of the other angles, let's say it's okay, just 60-degree angle. Now, what is the cosine theta value of 60-degree angle? It is 0.5. Oops. Here we go. So we can mainly say, okay, if we, for instance, okay, we're scanning at, let's say it's okay, a 60-degree angle, this whole thing here was multiplied by 0.5. Did you girls get that?
Yeah.
Okay. So we can mainly say, okay, Doppler shift was not directly, is not going to be as okay, directly proportional to the angle between the beam and, okay, as direction of blood flow. Because I mean, I said, okay, as 0-degree angle had been, okay, made it all 0. 180 would have made it, okay, as 180 degrees or 180 times greater is going to be the cosine or the cosine theta value of each individual angle. That is going to be as okay put into the equation. So it's going to be that okay as your Doppler shift is directly proportional to the cosine theta angle value of the angles. Where we could say it's okay 0 degree and 180 degrees had okay as cosine theta value of respectively 1 and -1. Where we could actually say that in this case, yes, okay, that the measured speed or measured velocity equals to the actual speed or actual velocity. Whereas in all the other angles, whether there was 30-degree angles, whether there was 60-degree angles, and the 30-degree angles we could say as okay 150 degree. With 60-degree angle we could say it's okay 120 degrees. Because these had respectively as okay cosine theta value of 0.57 plus for the 30 and minus for the 150. Right. Likewise here. These has okay a value of 0.5 and minus 0.5 respectively for 60 degrees and 120 degrees. So here, yes, okay, you can see the Doppler shift at these angles here are going to be half of what it would have been at 0 degrees and or 180 degrees. Did you girls get that? So in your book, if you look on page 309, do you guys have your books open?
Yes.
At the very bottom of page 309, you see something written in, okay, that light purple or whatever. That the measured velocity equals to the true velocity time cosine theta. Okay. And yes, okay, all the explanation for that is given on page 310. where we say, yes, okay, if the true velocity, for instance, was, let's say it's okay in all instances here, we say, okay, say 2 centimeters per second or 20 centimeters per second. If our angle of scanning was 100, now was, let's say 1 or 180, both of those had, okay, as cosine theta values of 1. Just one was +1, which was 0 degree. The other was -1, which was, okay, as 180. But you can mainly say that, okay, as if our actual velocity was 20 centimeters by, or 20 centimeters per second, and we multiply that by 1, because that was the cosine theta value at a 0 degree angle or 180 degree angle. Our measured velocity is still going to be 20 centimeters per second. Did you ladies get that? Did that make sense? Yes, ladies.
I have
Yeah.
a question.
Yes, Nikki.
I have a question.
Okay.
Would it ever be a negative value because like 180 degrees is a negative? Or would you
Of course,
always multiply it
if
by
we
one?
had, okay, because my dear, listen. Of course, it can be a negative value because we ended up having a negative Doppler shift. What did that negative Doppler shift mean? It just meant that, okay, the direction in which the blood was flowing was in a direction away from the angle from which we were scanning, right? Right there.
Yes.
Okay. So we can mainly say as, okay, if this was your blood vessel, right?
Mm-hmm.
Do you agree that this is a blood vessel?
Yes.
Okay. Okay. That's okay. And we just fill it up with blood. Let's just say that, okay, as for the red instance, we say it's okay, the blood is flowing this way here. Okay. What would that mean? Because that's okay, as mark our 90 degree here, because okay, this 90 degree angle here is going to be equal to 0, right? Clear?
Mm-hmm.
Good. Now, if our transducers were over here, at a 0 degree angle, at a 30 degree angle, or let's see, it's okay, at a 60 degree angle. Right, okay. But you can mainly say, as okay, since we are over here, yes, okay, the blood flows towards the transducers or towards the angle at which we are scanning, right? So in this case, yes, okay, they will all be positive Doppler shifts. Did that make sense?
Yes. I was just saying for the equation, you said measured velocity equals the true velocity times the cosine.
Yeah, okay.
So when you do like 180 degrees, you would
Okay,
still
listen.
multiply -1, right?
You just multiply by -1.
Okay, yeah, that's what I was asking.
So
Sorry.
that's how you are actually, it's okay, it just becomes, well, okay, as you multiply 20, well, you can say it's okay, -1. But you can say 20 multiplied by 1 is still 20, right?
Yes.
But then you just get a negative.
Okay.
Did that make sense?
Yes, thank you.
No problem there. Okay, Nikki, you had a question, I guess? Nicole?
No, I don't. I just say that I understand.
Okay, dear. So, right, okay. But that's just okay, yes. Okay. So we're okay. Okay. We can say yes, okay, we had the same, yes, okay, velocity. The velocity of the blood in the blood vessel. But let's say it's okay that we scan it from, let's say it's okay, a different angle now. Let's say it's okay. Just not to make it as okay, too complicated. We say it's okay, we scan it from, let's say, a 60-degree angle. I made it okay, just to yes, okay. We can say confirm what Dr. Ramos just asked. Yes, okay. The same 150, 120 degrees as well. Now here is okay. What is it that okay? It's okay. Our measure velocity, the true velocity was still 20 centimeters per second, right? But then yes, okay. If you multiply by yes, okay, the cosine theta value of 60 degrees. What was that? 0.5, right? That is mainly going to cause that. That's mainly that's okay. Going to give us okay as a measure velocity. Now 0.5 is mainly as okay. Is that the same as saying half? So yes, okay. Your measure velocity is going to be as okay 10 centimeters per second. Where okay, if you scan it from let's say it's okay 120 degrees. Now the cosine theta value of 120 degrees is minus 0.5. So what do we get? Well, okay, the true velocity of the blood was still 20 centimeters. But now, yes, okay, just multiplied by minus 0.5. Well, 20 multiplied by 0.5 or half is still going to, yes, okay, become 10 centimeters per second, right? But mainly because it was a negative cosine theta value, we have a negative Doppler shift. So that's why we mean it says, okay, the measured velocity is actually going to be a product of the true velocity, the actual velocity of blood, times the cosine theta value of the angles between your beam of the ultrasound and the direction of the blood flow. Because it's the same transducer. No, sorry. You can say it's okay, the same blood vessel. The blood is flowing in the same direction. Okay, this was positive. But it's okay if we scan from, let's say it's okay, over here at 120 or 150 and 180 degree angles. You can see, right? This is the direction from which we are scanning. And if I'm standing over here and somebody is moving in this direction, they are moving away from me, right? Okay, so that was how, yes, okay, all these, yes, okay, angles which were greater than 90 had negative cosine theta values. Did you girls get that? But if we take, yes, okay, the same transducer, but say, well, okay, if we change the direction of which the blood flows, let's say, yes, okay, now the blood flows here like this. Now, in that instance, well, okay, this, if you scan from here, that's going to be 180 degrees. This will become 150 degrees. This will become, yes, okay, 120 degrees, and 90 degrees is 90 degrees. This will then be, yes, okay, your 60. This will be your 30, and this will be your 0. Did that make sense? Right? Because now we can say it's okay for, if you say that the blood is flowing in the direction of the green, light green. Well, okay, if this is where we are scanning from, yes, okay, the blood flows towards us, right? Whereas, okay, we have been scanning from over here. At any of these angles, the blood will flow away from us. Did you ladies get that? Or we can stand on the street and look at what, okay, yes, what may be positive for me will be negative for you. Or negative for me will be positive for you. I said that. Did you take a picture today?
No.
Vamos a ver a tu base. Because if this is a two-way street, well, that's okay, a two-way traffic street. Now this is me. And this is you. Okay. Not the rush hour, me and you. Have you seen that scene? Me is you and he is me,
Yeah.
right? Okay. But let's just say, yes, okay, in one lane, it's okay, on one side of the street, the traffic may be running like this. Right? So yes, okay. For you, yes, okay, that will be positive, and for me, that will be negative, right? Right? Because it's running away from me or it's running towards you. Whereas, okay, on the other side of the street, well, okay, yes. Hopefully, yes, okay, the traffic will be running this way. Unless you have a ghost motorist who is driving in the wrong direction. So it's okay for that. This will be positive for me, and okay, it will be negative for you. So the thing that you need to understand is that, okay, yes, this is all about, okay, a relationship between the beam and the direction of the blood flow. Okay, girls? Okay. Now, what you will see when we yes, okay, on our system turn on our Doppler functions is that we'll be able to, yes, okay, adjust the angles or steer the angle of the beam. Either steer like this, steer like this, or steer like this. Okay, guys. Okay. So how is Doppler going so far? Be honest, guys. Don't sugarcoat it. Are you
It's a
getting it?
lot.
It's a lot.
It's a lot. Okay. Okay. But as I said, well, okay, you don't have to memorize the Doppler shift equation by heart. But I told you, yes, okay, it would be a good idea if you know the relationships. Right, okay. The main is, okay, just are, okay, pretty much, okay, two major relationships. The velocity of blood and the transducer angle. They are going to be vital. 2 is fixed, so there's no relationship in there, right? 2 is 2. Right, okay. But please, yes, okay, is the cosine theta value of the angles. It's not the angle, it's the cosine theta value. But is that something that you girls will be required to calculate? No. Just remember this much. 0 degree and 180 degree measure velocity is true velocity. Because the cosine theta value of those two were 1, 1. Whereas for the others, yes, okay, the measured velocity is going to be, yes, okay, just a fraction or part of the total velocity or actual velocity or true velocity. Because the theta value of any other angle than 0 and 180 are fractions. 0.87 is just the same as, okay, saying 87 cents. So it's not a dollar. Right, okay. 0.5 is just the same as saying it's okay, 50 cents. Or half. And 0 is 0. Okay. So please make sure that, okay, as you are 100% sure on that one, that, okay, as don't keep a 90 degree angle between the beam and the direction of the blood flow, because you will get a Doppler shift that is equal to. So yes, okay, girls, you got some pages to read on. Okay. So, and okay, if that wasn't enough, ladies, tomorrow I would like that you guys know, yes, okay, what transducers are. And if you can't remember everything about transducers, just remember 2 things. What is a continuous wave transducer versus a pulsed wave transducer? Clear? And those of you who, yes, okay, now. So we made, yes, okay, are going to take up, yes, okay, the different kind of transducers. This means there's going to be 2 transducers. And there's going to be, yes, okay, 3 kind of Doppler readings. Which have their own advantages and disadvantages. Okay? And please make sure that you know the consequences of your backing material. Okay, girls? Can anybody remember what the consequences of your backing material were?
Doesn't it lessen like the ringing?
Mm,
Lessens the vibrations.
we had 3 consequences of the backing material. They are written in P and they are written in chapter number 8. Reduced sensitivity, greater bandwidth, and low Q factor. Those were your consequences of the, what the blue call it, backing material. Jennifer,
Yes.
lesser ringing was mainly as okay what we just meant by less number of cycles per pulse.
Oh, okay.
Okay, dear?
Mhm.
Okay, so less number of cycles per pulse. That was what we meant by less ringing. Okay, ladies. Now, have any of you started your revisions? Or done any revision during the vacation? That silence kills me. Okay, girls, it's never too late. You still have, okay, approximately 3 weeks left to start, right? Yes, my dear?
So our final is still going to be on the 22nd, no matter what.
Your final, yes, okay. I may change the weather. I'll be able to change the weather. But I cannot change your final date.
Okay.
Okay. Anything else? Okay, girls. So, that's okay. Hopefully tomorrow is okay. We will take up the transducers and Dopplers. Okay. And then we will just go on with, okay, as some other small spread. Yes, my dear?
Sorry, I thought I muted myself. Did we go over sound beam direction and flow directions? I feel like
Did we do that?
did
What
we?
all that cosine theta angle shit about?
Oh, okay.
Oh,
I thought, sorry. Because I'm like, I don't,
no,
never mind.
that's what it was. That's all what it was about, my dear.
Okay.
Or you still want to get back on the highway? Okay. That was all that, okay, as that cosine theta value and all that. That was all about that. Okay, girls, but tomorrow is going to be a little tough day, okay? And after that, yes, okay. Well, okay, then we just have aliasing, which is, well, okay, not really that difficult. But it's one of the majors, okay, bad boys of, of Doppler. Okay. And then what else will we have? That's okay. Then I just, okay, some more technical topics. Small, which I mean, it's okay, related to, you can say it's okay, the equipment. Okay, girls, I guess I see you ladies tomorrow unless somebody have a question. Okay. What kind of Doppler shift do you have if the reflected frequency is greater than the transmitted?
Positive.
Positive Doppler shift. Very good. Okay. Okay. What is the relationship between frequency and axial resolution? Okay, let me ask it this way. Will a high frequency transducer have a good or bad axial resolution?
Or bad?
It's good because high frequency is better resolution, right?
Which resolution?
Forget that.
Why better axial resolution? Because of a shorter spatial pulse length. Because of a shorter wavelength. That's why it's okay, higher frequency transducers are ideal for diagnostic imaging. Okay. What is the effect of sector size upon your temporal resolution? Don't look so sad, girls. Okay, let me give you a sector size. What if you have a small sector size where you have a good or bad temporal resolution?
A good temporal.
A good temporal resolution, right? Okay, good. You know this stuff, you just choose not to answer. I don't know why, but in your B mode, what is expressed along the y-axis? In B mode, what is expressed along the y-axis? Y as in U.
Is it the amplitude?
No,
Nothing is expressed on it.
nothing. Your B mode doesn't have the y-axis.
That's the one that has the Z axis, right?
That's the one that goes with the Z.
Okay.
And the Z is your amplitude or the brightness. Of course, it's not every question that I ask that has a definite answer. Okay. That's fine. Okay, girls. I guess I see you ladies tomorrow with some more Doppler. Okay. Now, please make sure that you read on these pages here that we did today. And okay, the main thing to understand or remember is, or we can say, okay, the takeaway points is the relationships. Okay. Okay, ladies,
Okay.
enjoy your day.
Thank you.
You're welcome, dear.
Thank you.
Okay, you're welcome.